everyone, and welcome back. Today we're going to be continuing our exploration of multivariate statistical analysis and discuss the very important study of multivariate multiple least squares linear regression. So before we get into the multivariate part of it, let's just make sure we understand the basics of the univariate multiple least squares regression analysis. So what is univariate least squares? So what we're going to do is we're going to be using one response variable, y. Now that's where things are going to change in the multivariate sense. But if we have one response variable, y, and let's assume we have chosen some predictor variables, say x1, x2, down to xp, where p is the number of predictors in this particular model, then if we can find these coefficients beta 0, beta 1, beta 2 down to beta p, then what we have is a linear regression model. So what makes it a least squares regression model? So keep in mind, we can represent this model in a matrix form. So if you have, for example, the predicted values y hat, keep in mind this is going to be an n by 1 vector, and this can be represented as our X matrix, which some people call the data matrix or the design matrix, which is going to be an n by p plus 1 matrix, because we have a sample of size n, and p plus 1 predictors because we have 1, 2, down to p, and also the intercept coefficient. So it's going to be an n by p plus 1 matrix, where the first column is usually always equal to 1 because we have 1 for that x0 variable, I guess you could say. And then we're going to have our coefficient vector, which is going to be beta hat, and beta hat in the system is going to be p plus 1. So p plus 1, and that's going to be a column vector, so it's going to be by 1. And then we're going to have our residual vector epsilon hat, which, as you already know, is going to be an n by 1 vector, right? So some people will just write this in matrix form as y hat is equal to x beta hat plus epsilon, where it's understood that y hat, x beta hat, and epsilon hat are all matrices and vectors respectively. Okay, so least squares regression. So least squares regression, because we haven't mentioned anything about least squares yet, tries to minimize the functional f of beta hat, right? Where f of beta hat, which is just some functional on the coefficients of beta, is trying to minimize the functional y minus y hat L2 norm squared. And we can write this instead as y minus our x beta hat matrix and vector, right? Because keep in mind, there are other functionals that you can minimize, not just this least squares approach, but there's also lasso, ridge, and Garat, and several other variations of matrix norm type of functionals, right? But least squares is usually the starting point for most linear models. So if you know anything about multiple linear regression via the least squares regression approach, then you know that the solution to this minimization problem is actually very, very nice. In particular, if you use some matrix calculus, you can actually find that this vector beta hat that minimizes this particular functional can be found explicitly as xt x inverse times xty. Right? So that would be the solution to this least squares regression problem. And keep in mind that this solution, which is a p plus 1 by 1 vector, contains all our estimates beta hat 0 down to beta hat p. So beta hat 0 is our intercept, and beta hat 1 through beta hat p is our coefficients for a linear regression model. So some theoretical things that you can prove, which we've proven already before, is that this beta hat vector is an unbiased estimate of this vector beta. Keep in mind that beta hat is a vector, not a number. So this ranges from beta hat 0 down to beta hat p. So that's a vector. So the expected value of a random vector, since those are a bunch of random variables, is also a vector as well. But it's a parameter vector, and this vector beta, keep in mind, is just the exact coefficients beta 0, beta 1, all the way down to, say, beta p. Right? So that's the expected value of beta hat, which implies that beta hat is an unbiased estimator of beta. So that's the first thing that's very important. But keep in mind, just because it's an unbiased estimator doesn't mean it has error associated to it. Keep in mind, one of the assumptions of the least squares multiple linear regression model is that the variance of y, given a particular variable x, and keep in mind that's a random vector, not necessarily a single variable, is going to be equal to, so I guess you could say x1, x2 down to xp, just to be a little bit more explicitly precise, is equal to sigma squared, where this sigma squared is a real valued constant, obviously greater than or equal to 0. But regardless of the x values that you observe, you should get a constant variance. This is usually what we refer to as the homostochasticity assumption, right? But as long as this assumption is met, or you assume that is met, that means the variance of this beta hat vector has a nice representation. Keep in mind, if beta hat is a random vector, the variance of a random vector will be a matrix, a parameter matrix. So explicitly, this can be represented as sigma squared, that constant that we're trying to get, times the matrix xtx inverse. Right, so that's the variance of beta hat. And keep in mind, since this is a random vector, technically this is a covariance matrix. So we can actually represent this as sigma, and I'm going to subscript that with beta because technically we have several covariance matrices going around in the multivariate sense. And keep in mind, since that is a covariance matrix, pretty much what you have here is a bunch of covariances between beta hat I and beta hat j, where the variances of each of those individual coefficients are located on the diagonal, and the covariances are on the off diagonal as well, right? So you have that symmetric matrix sigma beta. All right. So another thing that you probably should know from the univariate case before you proceed is the variance of our residuals. Keep in mind, looking at the residuals is not necessarily nice because the variances should not be constant. Actually, they depend on what we call the leverage of the value. Because if it was just constant, it would just be sigma squared times nothing. But in particular, it's times I minus h, where h is the associated hat matrix. And in case you don't remember the hat matrix, h is the matrix x times xtx inverse times xt. And the reason we call it the hat matrix is because it puts the hat on the y, right? So hy is equal to y hat. So we call it the hat matrix, right? So that's pretty much what we have going on here, and that is commonly used to find like standardized residuals, which are usually very important in the analysis structure. So those are the things that you definitely should know from the univariate multiple least squares regression theory. So now let's see if we can state what our main goal is for today. So can we have multiple response variables? Can we have multiple response variables? Let's call them, say, yk, where k is equal to 1, 2, down to, let's say, d, right? That are potentially dependent on one another. Right? So, for example, let's assume that you have happiness, and you're trying to predict happiness with age and also money. Let's also assume that you're trying to predict height with age and money. And let's assume happiness and height are correlated with one another. Now, if you believe that happiness and height are independent random variables, then technically you could do separate multiple linear regression models on happiness and another multiple regression model on height. And by pretending that these variables, y1 and y2, are independent. But it's possible that height and happiness are dependent variables, so multivariate multiple linear regression will take that into account as well. So what would be our linear structure or setup for our models? So pretty much what we're going to have is we're going to have a y hat matrix. Originally it was m by 1, but now it's going to be an n by d matrix. And then we're going to have our design matrix x, which is going to be the same exact size because we're just going to having the same amount of data, just more responses. So this is still going to be an m by p plus 1. And that's going to be multiplied by a beta hat matrix, which was going to be a p plus 1 by 1, but now it's by d. And then we're also going to have our residual matrix, which is going to be an n by d matrix, right? So that is our matrix structure for our multivariate multiple linear regression, which I'm going to call MMLR, right? So if we were to look at this, what are we going to have? So we're obviously going to have a y hat 1, which is equal to a beta hat 1, 0, so that's our intercept for our first model, and then beta hat 1, 1 times x1 plus beta hat 1, 2 times x2, all the way down to beta hat 1, and then d, or p actually, times xp. And then we're going to continue that all the way down to the last response, which is going to be y hat d, and that's going to be equal to beta hat 1 d, beta hat d 0 actually, so beta hat d 0, and then beta hat d 1 x1 plus beta hat d 2 x2, all the way down to beta hat d p xp, right? So that would be the written out version of this matrix structure. So that's what we're going to be solving. So let's get right into the math of see how we can build all of our metrics in statistical analysis for this multivariate multiple linear regression problem. Let's view a couple mechanisms from linear algebra that you may or may not have encountered before. The first of them being vectorization of matrices. So what does it mean to vectorize a matrix? So the vectorization, which I'm going to abbreviate by VEC of a matrix, let's say 3, 5, 2, 7, will map any matrix you feed it into a column vector by stacking the columns on top of each other. So for example, our columns are 3, 2, and 5, 7. So what we're going to do is we're going to just create another vector. Keep in mind this is a 2 by 2 matrix, and we're going to send this to a vector which is going to be a 4 by 1 vector by stacking the columns on top of each other. So this is going to be the vector 3, 2, 5, 7. And that's all vectorization of matrices is. So very, very simple. So what we're going to do is we're going to vectorize our matrix representation of our multivariate multiple linear regression model. So the first thing that we need to deal with is this y hat n by d matrix. So keep in mind we're going to have y1, y2 down to ym, y1, y2 down to ym, all the way down to y1, y2 down to yn, but they're going to be for different d response variables. So this is for the first response variable, the second response variable, and this is the last and final d response variable. So what we're going to do when we vectorize this particular matrix, we're going to have that column, and that column stacked on top of each other. So once we vectorize that, so the vectorization of y hat, which I'm going to denote by y hat with a v, so it's like an intersectional v hat looking thing. So this is going to be a column vector of some length, and we're going to have what? So we're going to have y1, y2 down to yn, and then we're going to have y1, y2 down to yn, and then we're going to have that all the way down to y1, y2 down to yn, right? So let's make our matrix just a little bit bigger so it's holding all of these values. So again, what are we looking at here? So this is associated to the first predictor, and that's associated to the response variable. That's our second response variable, and that is the last response variable response values at the very end or tail of that vectorized matrix, which is just a vector. So what is the size of this particular object? Keep in mind we're going to have n rows and d columns here. That means this is going to be equal to an n times d row by 1 vector, right? So that's the first thing that we need to deal with. Now, keep in mind our epsilon hat n by d vector will be similarly represented. So once we vectorize this epsilon hat, we're going to have an epsilon hat v vector, which is going to be equal to, again, an nd by 1 vector, right? Which has this pretty much similar structure. You just replace these y's with epsilons, and we're going to have just residuals stacked on top of each other for each response variable, y1 down to yd. Now, before we get into the last piece of our puzzle, because there's 3 pieces in our puzzle, we have our y hat, our epsilon hat, and the more complicated term x beta hat. So how are we going to vectorize the product of 2 matrices? So a couple very important things associated to the vectorization that I want to mention here. So a couple theorems that you should be able to prove on your own if you have a strong linear background, is that the vectorization of a plus b will be equal to the vectorization of A plus the vectorization of B, right? So that's the very first theorem that you definitely should know. Now, the next important operator that I want to mention, just in case you haven't learned this, is Kronecker products. So we're going to let cross K, which I'm just going to be using cross because I'm not going to be using outer products or other type of tensor products in this discussion. So this is going to be denoting the Kronecker product, be the Kronecker product operator. And if you've never learned about Kronecker products, let me briefly give you a crash course in them. So let's assume that I have a Kronecker product with B. And let's assume A is an M by N and B is a K by L matrix. So you can Kronecker product any two matrices regardless of their size, and you're always going to get another matrix back. So the first matrix of interest is going to be A, so you should already know what A looks like. So what A is going to look at is going to be A11, A12, all the way down to A1n, and then A21, A22, down to A2n, and that's going to continue all the way down to AM1, AM2, all the way down to AMN. Right? So that's what A would look like. And now what we're going to do is we're going to put that matrix B next to each of those elements. Keep in mind, B is a matrix, not a number, so that means this is just a block matrix, where a block is sitting in each of those cells. Right? So that means this object right here is going to be a K by L matrix of B scaled by constant A11. And this cell right here is going to be another K by L matrix, which is just going to be the matrix B scaled by constant A12, and let's continue all the way down to AMN times matrix B. So once we have that, then what do we have? Well, let's see how many rows and columns that we have. So what is the number of rows and columns of B? So B has K rows in it. That means there's K rows here, there's K rows there, there's K rows all the way down here, and then there's K rows on that last row in this block matrix. And keep in mind, there are M rows in the A matrix, so that means there are going to be M by K rows total in the Kronecker product of this particular matrix. And keep in mind, each of these columns of this block matrix is dictated by the number of columns in the matrix B, which is going to be L. So we're going to have L of those, L of those, L of each of those, and then we're going to have L columns in that last column of the block matrix. And keep in mind, how many columns of A do we have? We have M of them. So we're going to have L times N of them as well. Right, so we can write that as N times L columns in the fully formed Kronecker product matrix. So we have MK rows and NL columns. Therefore, this entire matrix, A Kronecker product with B, is going to be an MK by NL matrix. Right? So that is how you can do Kronecker products with matrices. And there's one very beautiful theorem associated to Kronecker products, and also it's connected to vectorizations, and it's going to be the following, and this is the one we're going to use in this multivariate multiple linear regression, and that's the vectorization of the product of A times B times C. And let's assume that the inner dimensions and the outer dimensions of A, B, C match such that this product is well defined. So this is going to be equal to C transpose Kronecker product with A times the vectorization of this matrix B. So in some sense, this switches in front, this is multiplied on the right of it, and then this middle matrix is vectorized. And I leave it for you to verify, in case you haven't encountered this, that the dimensions of this, if it matches, does indeed match the dimensions of that once you vectorize that associated matrix. And that's a very, very beautiful exercise in case you haven't already done so. So now that we've reviewed some vectorization in Kronecker product linear algebra, let's get back to our multivariate multiple linear regression problem. So what we're going to do is we're going to vectorize both sides of this multiple multivariate equation. Keep in mind, y hat is going to be a matrix, epsilon hat is going to be a matrix, and x times beta hat will also be a matrix as well. beta hat being a matrix 2. So if two matrices are equal, their vectorization will also be equal to, so we're going to have the vectorization of y hat will be equal to the vectorization of x beta hat plus epsilon hat. As already mentioned, vectorization can distribute over addition, so that's not going to be a big deal. On the left-hand side, we're going to have y hat vectorized will be equal to the vectorization of x beta hat plus the vectorization of epsilon hat, which is going to be epsilon hat vectorized. Now we have this object here. Now remember the theorem associated to vectorization of product of matrices had 3 matrices, so what we can actually do is introduce an identity matrix of some appropriate size into this product so that we can apply that identity. So what I'm actually going to do is I'm going to take that x beta hat and I'm going to multiply it by a identity matrix, and I'm going to multiply it on the right hand side. Now, let's make sure that the dimensions all match up. So we have an x, which is a n by p plus 1 matrix. That's going to be multiplied by a b hat, which is going to be a p plus 1 by d matrix. So if I multiply that by an identity matrix, it needs to be a d by d identity matrix. And then we're going to have our residual vector vectorized. So now this is going to be like our A, this is going to be like our B, and this is going to be like our C, right? Which is going to turn it into C transpose Kronecker product with A times the vectorization of our beta hat vector. So once we actually write that out, what are we going to have? So we're going to have y hat vectorized will be equal to the transpose of that Kronecker product with x, and then times the vectorization of beta hat, and plus the vectorization of our residual vector. Keep in mind I is a symmetric matrix, so I transpose will be equal to I, so this is going to be just y hat vectorized will be equal to I Kronecker product with x, and then times the vectorization of beta hat, which I'm just going to write as beta hat vectorized, so beta hat vectorized plus epsilon hat vectorized. And we have this very beautiful identity. So it's almost like an x beta hat, but we have x Kronecker product with I. So what exactly is this object? So we're going to be taking the identity matrix, so the identity matrix Kronecker product with x. So keep in mind, identity matrix has 1 on the diagonals and 0 everywhere else. So we're going to have 1, 1, all the way down to 1, and then we're going to take x and we're going to just multiply them by those scalars. And keep in mind we have zeros everywhere else, right? So what we have here is matrices on the diagonals, in particular the same matrix, and 0 elsewhere. And keep in mind these are 0 matrices, not 0 numbers. This is usually what we refer to as a block diagonal matrix. So since it's pretty much just a matrix with x's in it, this still is sort of like x only, right? And I'm going to put a d above that. So it's a diagonalized version, or it's a diagonal matrix with x's on the diagonals, right? So that's what this d is going to be representing, right? So that means we just have y hat vectorized is going to be equal to a diagonal block matrix with x on the diagonals times beta hat vectorized plus the epsilon hat vectorized as well. So this is just a y is equal to x beta plus epsilon thing, which is just a multiple linear regression model, right? It's just a multiple linear regression model because y hat vectorized is just a vector. Beta hat vectorized is just a vector. X is just a matrix, and epsilon hat vector is just a vector, right? So this is just a multiple linear regression model, just like before. So we should be able to solve it using the same vector calculus as we did when we proved multiple linear regression, beta hat formula for least squares, right? So again, what we're going to do if we're going to use a least squares, so least squares is going to minimize this functional f beta hat. Keep in mind, actually, this is going to be a beta hat vectorized, and this is going to be equal to the norm of y hat minus x d beta hat. Let's use capital D to stay consistent with notation as well, right? So that's going to be the diagonal matrix with x on the diagonals times our beta hat vectorized 2 squared. right? So our goal is to simplify this, and keep in mind actually y, that should be a matrix. This is a matrix, that's a matrix, matrix minus matrix, and we're trying to minimize this particular function, right? Actually, no, that's going to be a vector. So we need to vectorize that thing there. Cool. So now we have a vector, actually. So vector, vector, and we can take the norm of a vector as usual, right? So keep in mind, what is this vectorized version of y? So that's the true values that y should be from our sample. So once we actually perform our vector calculus, what are we going to get? Right? So we're obviously going to have some beta hat thing, and what you can actually find, and I'll leave this as an exercise to you in case you are interested, but you're actually going to have beta hat vectorized is going to be equal to the Kronecker product of the identity matrix with your xtx inverse, and then x matrix, important not xt there, right? So you're going to have that matrix multiplied by the vectorization of y. Right? So we don't want the vectorized version, we want the unvectorized version, right? So what we're going to have is we're going to have the unvectorized version of beta hat v, which will be equal to the unvectorized version of this object, I Kronecker product with xtx inverse and x, and then that's going to be, oh, let's not forget our lonely little vectorized y version there. So let's throw that there, right? So one can also do as an exercise that once you have that, you're going to have beta hat, the matrix, will actually just be equal to xtx inverse times xty. You're going to have this result. Now, this exercise, not super trivial to prove, but it is indeed true. Now, if you remember the formula for the multiple linear regression univariate case, it's the same formula as before. The only difference is this is not a vector, it's a matrix. This also isn't a vector, that's a matrix as well. So these are both matrices now, and that's the solution to the multivariate multiple least squares linear regression problem. So it's almost the same exact thing. So instead of having a vector full of coefficients, now you're going to have a matrix of coefficients by just changing your code with y to your matrix of response values for each of your response variables, y1 down to yd. And I think that's really amazing. Now that we've proven that wonderful result, now let's mention some theoretical things that you definitely would know when actually performing a multivariate multiple least squares linear regression model. So since we now have this beta hat matrix, some things that you could easily prove without minimal theory is that going to be the expected value of this beta hat matrix will be equal to this beta. Keep in mind this is now a matrix. Right, so the expected value of a random matrix will be a parameter matrix, and this is going to be equal to beta. Now the variance of this matrix, this is where things get a little tricky to deal with, but no worries. So one of the assumptions of the multivariate multiple linear regression model are going to be the following. In particular, this these values, in particular y, should be multivariate normal. Right? So these variables x should be multivariate normal. So that's the first thing. The second is that the observations between y's, so y in particular x, should be independent of one another. So yi and yxj must be independent. The third is that the variance of these variables should be constant regardless of the values that you're looking at. Keep in mind y is now a matrix, so this also needs to be a matrix as well. Right? So that's going to be our covariance matrix. So that's going to be our constant covariance matrix. Right? So we're going to have these three assumptions. And sometimes people throw in some extra things as well associated to linearity of means. Actually, that's one of the most important things, so let's definitely not forget that. So fourth is that the expected value of y, given a particular value of x, should be equal to x beta for some beta. Right? Those are the four common assumptions for multivariate multiple linear regression. So if we assume homoscedasticity or multivariate homoscedasticity for your linear regression model, then one can prove that the variance of beta hat actually has a very similar structure to that of the univariate case, but it's going to be that constant covariance matrix Kronecker product with the matrix XTX inverse. Right? So that's going to be the variance of beta hat. And I'll leave to you to sort of explore where to find what you want in that particular thing. But that's going to contain your covariances of your variables, also with respect to your y's as well. Right? So that's going to be very, very useful. Right? But keep in mind, if they are independent y's, then pretty much all you really care about is those diagonal entries of this particular Kronecker product. Also, another very useful thing, if you want to standardize your multivariate residuals, the variance of epsilon hat will be equal to that sigma matrix, Kronecker product, with the identity matrix minus the hat matrix, and the hat matrix, as usual, will follow the same exact structure. It'll be x times xts inverse times xt. Same exact hat matrix as the univariate case, and that's where you're going to be looking for your leverages, which as usual are located on the diagonals of your hat matrix. Now, what type of metrics are there out there for analyzing or assessing the appropriateness of a multiple linear regression model? Keep in mind, back in the univariate case, we had, the R squared value, we had our F test statistic, and we have several things for our multivariate case as well. So let me mention just a few of them. Now, if you do remember the relationship between linear regression and ANOVAs, multivariate linear regression and MANOVAs have a very similar relationship as well, so they can be assessed and tested in a similar fashion as well. So, as usual, we're going to have, just like the MANOVA case, we're going to have an S sigma T matrix, we're going to have an S sigma E matrix, and we're also going to have an S sigma M matrix, and when you add up your S sigma E and your S sigma M matrix, you will get your S sigma T matrix as well. In the multivariate world, these are actually going to be very, very interesting looking, and I'll give you the formulas for them and leave as exercises for you to prove. But the S sigma T will be equal to Y transpose times the identity matrix minus 1 over the sample size times a matrix full of 1s times your Y. And you should be able to prove that when D is equal to 1, this is precisely equal to your variance of every one, all of your response values, times n minus 1. So for the S sigma E matrix, you're going to also have Y transpose times another matrix, I minus your hat matrix times your Y at the end. And then we're going to have Y transpose times your hat matrix minus 1 over n times our 1 matrix 1. And then that's going to be multiplied for your matrix 1. Actually, what I want to do is I want to put a little hat underneath to emphasize that that is actually a matrix, else you won't be able to subtract it from I and H. Right? Now, from these two identities, you should be able to show that this plus this should be equal to S sigma T quite directly. And then, usually from these, you can, since we have our S sigma T, S sigma E, and S sigma M mixtures, then maybe you want to do some of your MANOVA matrices hypothesis testing, such as Hatalian-Lowry, your Roy, your Wilks, your Pillai, or whatever things you might seem appropriate, or maybe even create your own. Now, in the ANOVA world, and our univariate multiple linear regression world, we looked at some MSMs, MSTs, and MSEs. So we actually can build them in our multiple case as well. So for example, M sigma T will be equal to S sigma T divided by n minus 1, but now we have D of those. So that would be the degrees of freedom for that particular matrix. And then we have our M sigma E, which is just going to be equal to our S sigma E matrix. Now, for our univariate case, that's going to be equal to M minus P minus 1, but now we have D of them as well. And then lastly, we have our M sigma M matrix. So M sigma M matrix will be equal to your S sigma M matrix, and the degrees of freedom of that was equal to the number of predictors you had, and now we have D of them for each of those predictors. So those would be our mean square matrices, and then it can start building your test statistics. So for example, a nice test statistic, F question mark stat, for our MSM over MSE, so that would be something that you would try and generalize. So what we would do is maybe replace MSM with M sigma M and MSE with M sigma E, invert it, and then maybe do the determinant of something like that. So for example, you could do the natural log of the determinant of M sigma M, and you can divide that by the determinant of, for example, M sigma E. That would be one object, or you could just divide those two determinants and then be done with it. Another possible thing you could look at is maybe the largest eigenvalue or the trace of, and you can maybe do the M sigma E, and then invert that, and then do, for example, M sigma M there. That would be another reasonable metric to look at because they all have that particular MSM over MSE structure. There are infinitely many variations, each with their different names. If you want to know some of them, definitely look back at our MANOVA discussion, and there was 5 that we looked at there. But since MANOVAs and multivariate linear regressions would be pretty much similar problems, at least up to some equivalencies, you could still in some sense use those methods. Just make your distribution matches as usual and make sure your assumptions for this follows as well. Keep in mind multivariate normality is required here, so you probably would have to start off with, say, a Heinz-Zerkler test to assess that. We also have homoscedasticity, which means you might have to start off with a box test for that, and also make sure independence is satisfied as best as you can. So those are some of the principles associated to multivariate multiple least squares linear regression and some of the metrics that are associated with it. Hope you enjoyed this video, and I'll see you in the next one. Take care.